Announcement I have is that homework 3 is released, and that's due next Tuesday. I will say that it's similar in length to homework 2, but it's due on Tuesday. So if you only really started homework 2 towards the end of the deadline, make sure to start homework 3 earlier because it'll take some time to get through it. After today's lecture, you will know everything you need to know to complete homework 3. In addition to that, as I mentioned last class, we have a note/guide called Data Frame Internals, which you can find from the sidebar of the course website, that talks about things like how to add columns to data frames and how to do it in a way that doesn't accidentally destroy data that already existed in your notebook. Totally separate, I wouldn't call this an announcement, but like I heard about this tool called 3 Blue 1 Brawn. Have other people heard about this? Okay, anyways, you go to the website and upload a PDF of anything, and it makes a video of LeBron James, that is, talking or summarizing that video. So I just put a clip, I took a PDF of last lecture and just uploaded it. I just figured out what it said.
This video will dive into the concept of aggregation in data science, focusing on grouping and pivoting techniques. The lesson is part of the practical data science course from winter 2025 provided by EEC's 398. Stay updated with the latest course announcements on ED. We'll start.
So listen up, stay updated on it.
It automatically subtitles it too.
Yeah, this is all automatic. I just uploaded a PDF of Monday's lecture and it did this. Yeah.
Is it free?
Yeah, totally free. 3 Blue 1 Brawn, put whatever PDF you want and it'll do it. Okay, so the plan for today's lecture is to start by recapping the group by method, which we spent all of Monday discussing. We will talk about pivot tables, which you can think of as kind of an extension of using group by. Then we will talk about how to merge two different data sets about the same individuals together. And there's some nice complex complex ways that we can analyze the behavior of merging that we will discuss together. And then lastly, talk about this idea of transforming, which sounds complicated, but it's really just the act of applying a function to every element of a series. And it turns out there are various ways you can do that, and some are more efficient than others, and we will talk about that in detail. So we'll start by loading in our Penguins data set from last class. Remember, the data frame we are working with has 333 rows, each of which corresponds to a different penguin in Antarctica, and for each penguin we have various pieces of information, like which island they live on. There are 3 islands, which species they are. The 3 species are Adelie, Chinstrap, and Gentoo, and then various numeric features about these penguins as well. Okay, so the key to remember is that the group by method at its core helps us answer questions that involve doing some calculation separately for each group. So anytime you see a question that's like, what is the group with the highest XYZ? Or find the median XYZ per group. Anytime you encounter a question that resembles that sort of structure, you're going to want to resort to the group by method, okay? And so the most common way you will use the group by method is you'll specify the column you want to group on, you'll pick a column you want to aggregate, and then you will follow that up with an aggregation method. So here I'm saying, hey, separately for each species, go to the bill length column and compute the median. And what I get back is a series indexed by species, giving me the median bill length for each species. Okay? And so remember, the way to interpret the call to dot group by species is, in English, separately for each species, do XYZ. And notice the index is automatically set to species, which happens whenever you're using an aggregation method. Now, as I'm about to show you, there are other ways we can use the group by method, and sometimes what we get back isn't indexed by species, but rather it kept entire rows of the original data frame intact. But at least in this most common structure where you provide an aggregation method, maybe I'll annotate median as being an aggregation method. You'll get back some structure, either a series or data frame, depending on if you asked it to aggregate one column or multiple columns, you'll get that back indexed by the thing you grouped on, which here is species. Okay? Now, the more advanced way, let's say, to use group by involves using one of those 4 special grouping methods. And there were 4 of them, and I summarized them on a grouping method cheat sheet, which is at the very end of last Monday's lecture. The 4 advanced grouping methods were ag, filter, transform, and apply. And they allow you to do more than just use built-in aggregation methods. So for example, I can do things like say, hey, separately for each species, go to the island column and find the most common value. Okay, how might we do that? As far as I know, there isn't a most common value series method already baked in. And so what I could do is use the ag grouping method and make my own function that says, hey, for all of these islands, when I'm looking at just one species, what I could do is call the value counts method on that series. So this will say how many of one particular species live on Dream Island, Torgerson Island, and Bisco Island, I believe was the 3rd one. And of all those, give me the most common. That is, give me the index corresponding to the largest value. And when I do that, you'll see it also gives me back a series indexed by species, and the value it gives me back is the result of calling this aggregation method on a series of island names for each particular species. So for example, this method takes something like, dream, Bisco, dream, ... And what it does is it takes that series, which contains all the island names separately for each species. So there's 3 times this aggregation method is called. It takes those island names and figures out which one is the most common. Finds the most common one. Okay? And then that was using ag, which at its core is similar to just using .median. We just made a custom aggregation method. But another one of these grouping methods we discussed was .filter, where we keep entire species, or more generally, entire groups that satisfy some condition as a group. So for instance, I could say, hey, give me back a new data frame with just the rows corresponding to species that have at least 100 penguins. And so when I do that, I give a function to .filter that takes in a data frame of all of the rows for a particular species and returns a single true or a single false. Okay, so this df that I've parameterized this lambda function by, it's going to correspond to a data frame of just the Adelie penguins and just the chinstraps and then just the Gen2s. And it has to take in that data frame and output a single true or a single false. And if I want to implement this condition, hey, keep just the species with at least 100 penguins, I can go to that species-specific data frame, look at its number of rows, which I get by .shape0, and check whether or not that's greater than 100 or greater than or equal to 100. In some species cases, that'll be true. Some species cases, that will be false. Notice I don't have 333 rows anymore. I have 265. Not 333, because one species has fewer than 100 penguins. Which species has fewer than 100 penguins? Can you tell just by looking at this? Chinstrap, yeah, because these rows have Adelies. That row has a Gen2, which means all the Gen2s have to be here, because it's keeping or excluding entire species, which means chinstraps are missing. Okay, any initial questions with our review of the group by method before we take it a little further? Justin.
The methods that we're going over here, are they only able to be used in conjunction with group by? Or if you, could you use them with just like a data frame or a series?
Filter only makes sense in the context of group by because its whole premise is which groups do we want to keep. If you want to just take a subset of rows, that's a query, which is not something that involves grouping. Yeah. Ag, you can actually use without grouping. You could like test it out in your notebook. Do like penguins, square brackets, bill depth, millimeters, .ag, and see what you could give it. That does actually work. And apply also works as well in ways I'll show you at the end of today's lecture. Filter is kind of a special case. It just only makes sense in the context of grouping. Good questions. All right, so one way in which we can take the idea of grouping one step further, and one that we had a few questions about on Monday, is what if we group on multiple columns? What would that mean? Well, as we saw before, when we group on a single column, what Pandas does is it creates several sub-data frames internally, one for each unique value in the column we told it to group on, right? So in this slide where we were grouping just on species, it thought about Adelies, chinstraps, and Gentoos separately. Okay, so whatever calculation we told it to do, it did it 3 times, once for each unique species. Well, when we group on multiple columns, it considers all unique combinations of those 2 columns. Okay, so here I told it not to group just on species, but group on species and island. And after I do that, I told it to go separately in all those combinations, go and look at the bill length column and go look at the bill depth column and compute the mean, which is why I have 2 columns in the data frame that's returned. Now here's a question for you. I told you that there are 3 unique species and 3 unique islands. 3 times 3 is 9. Why does this data frame not have 9 rows? Why does it only have 5? Justin.
Chinstrap and Gentoo penguins don't appear on the 2 missing islands in each of their rows.
Exactly. It's because chinstrap penguins only exist on 1 island. Same with Gentoo penguins. They also only exist on 1 island. Not all 3. So in other words, while there are theoretically 9 possible combinations of species and island, our actual data set didn't have instances of all 9 of those combinations. Rather, it only had instances of these 5 combinations. Do we agree? Okay. Now, you may notice that this data frame has a strange looking index over here. It actually only has 2 columns, and it has what is called a multi-index. Okay? And a multi-index, you know, I could spend 10 minutes showing you how to work with it, but the easier solution is to just reset the index after you group on multiple columns. When you reset the index, you get back a new data frame in which the index is reset to 0, 1, 2, and so on and so forth. But the things that were in the index become regular columns. So this is easier to work with in terms of querying, as we've seen before. Okay, what questions do we have with grouping on multiple columns? While I get my iPad charger. Okay, so now that we're comfortable with the idea of grouping on a single column and we know about grouping on multiple columns, I want to show you an extension or a different way to think about grouping on multiple columns, and that is creating a pivot table. Okay? Pivot tables are a table format that display numbers in a easily readable format for humans. Okay? And these are really popular in business applications. Like if you go this summer and are some sort of like analyst intern, you'll make a lot of pivot tables. Maybe in Excel, but now you know how to do it in Pandas as well. Okay? Another place you find pivot tables a lot are in government data. Okay? And that's because they just nicely summarize lots of pieces of information in one place. Okay? So for example, the pivot table we're looking at here tells us the average or mean body mass of all penguins for each of these combinations of species and sex. So So for instance, it's telling me the average body mass of all female Gen 2 penguins in my data set was 4,679 grams. Okay? Or the average body mass of all male Adelie penguins was 4,043 grams. Okay? So it's essentially showing me the results of grouping on multiple columns. It's just formatted in a different way. Like it took the results of grouping on 2 columns, which would otherwise be really long, and it kind of squished it into a square. Okay, that's easier for us to read. Do we agree? Okay, so how do we actually make a pivot table? Well, we use the pivot table method. Okay, and it has several arguments. You have to use 4 arguments to get it to work. And a summarized version of the documentation is here, but let me walk through it with you. Okay, so let's try and recreate the graph or the pivot table we had on the previous slide. That is the average body mass for every combination of species and sex. So one of the first things we need to decide, if we go back to this example, is what is going to constitute the rows of the new data frame and what is going to constitute the columns. Notice here, the index became species. And there's 1 column per value in the original sex column. Okay, that was an intentional choice we made. You could imagine us rotating this data frame and have 1 row per sex and 1 column per species. And that would be a totally fine way of doing it as well. Instead of having 3 rows and 2 columns, we would have 2 rows and 3 columns. Okay, both of those would be valid. We just need to decide which of these 2 we want to do. Okay, so in an effort to replicate exactly what we have going on here, I'm going to tell pivot table, hey, make it so that I have 1 row per species, 1 column per sex. Okay, and the way you do that, going back here, is to go to your original data frame called penguins, use the pivot table method, and say, hey, in the new data frame, the index is now going to be species. So you use the index equals argument. Let me make this bigger here. Then you say, hey, in this new pivot table you're cooking up, make the columns the unique sex values. Okay, so you say columns equals that. Then you need to say what numbers are actually going to be in the grid. And in this case, the numbers in the grid are the average body masses. So what column do those come from? Well, they come from the body mass column of the original data frame. So I say values equals body mass G. And then finally, I tell it how to combine all the body masses for each of these combinations, right? And so this is essentially asking me to say, hey, how are you going to aggregate all of the body masses once you pick a particular species and sex? And this is the same general idea as using an aggregation method when we first looked at grouping. And so here, agfunc should be something like mean or median or min or max. Okay? And the way that they happen to implement it is such that the pivot table method knows about the most common aggregation methods you would want to use, and you specify them as strings. Okay? So mean, median, min, max all work. And as you might imagine, you can make a custom aggregation function and put that as an argument here as well if you wanted to. But for now, I'll illustrate how to do this using mean. Okay? And now we have the exact same pivot table that we had on the previous slide, and this was the syntax to create it. Now, I'll point out that we could have done this using group by, right? I could have said, hey, go and group on both species and sex, then go to the body mass column, and for each of those combinations, take the mean body mass. Okay? Both the data frame up there and the series down here, which I can render for you as a data frame if you would like, by putting double square brackets or a list of column names, both of these show me the same information. Okay? But which one is easier to read? Particularly if you had to convey the information to someone else who isn't, an avid pandas user like yourself. Which one would you prefer? Yeah, the pivot table. Okay, so that's all the pivot table is, just a nicer way of formatting the result of grouping by 2 categorical columns. Hector.
I was just curious about the data frame or the table we build if we do group by. This is just a weird nitpicking question, but when you hover your mouse over it, is there a reason why like, cause it helps with intuitiveness, like for example, if you hover over the mouse like chin strap, it'll only highlight female, and if you swap to male, it doesn't like swap over. I don't know, if you hover over.
Here, yeah, let's try that. You're talking about this?
Yeah, like if it looks at male, like if you do chin strap.
Oh, I see what you mean.
Yeah.
That's just a quirk of how the HTML rendering, like how they decide to implement it in Jupyter Notebooks. It may be different in VS Code or Jupyter Lab. So, see.
Oh, what do the double brackets mean again?
So when I had just single brackets, I'm telling it to aggregate just a single column. And anytime I want to extract a single column, I provide it just as a single string. So this is creating a series group by object. Remember, if I get rid of this, individual column creates a series group by object. Anytime I want to specify multiple columns, I provide a list of column names as an input to whatever indexing object I'm using. This works the same way if you just have the original data frame and want to select one column versus multiple columns. If you put a single column name in quotes, you get back a series. If you put multiple column names in a list of strings, you get back a data frame. But you can provide a list of column names and only have one thing in the list, and you still get back a data frame.
So essentially pass them a list
Yes.
to create a data frame.
Exactly. Exactly. All right, let's take a look at another example. So the previous example we saw found the average body mass for different combinations of species and sex. Now I want to find the number of penguins per island and species. Okay? Now note that, again, this doesn't really require a pivot table. What I could do is I could go to group by, our old friend, and say, hey, for every combination of species and island, use the size aggregation method. We saw this last class. It's kind of like a clone of value counts, but it works a slightly different way than value counts. And value counts does actually work here in ways that are kind of strange. You can do this. You can say go value counts the combinations of these two columns. Okay? So here we do have the answer to the question that was at the top of the slide. Find the number of penguins for every combination of species and island. Okay? What's the difference between these two?
Different ways.
Yeah, they're sorted differently, and we saw this last class. Okay, value counts by default sorts in descending order of count. Anytime you group by, the index gets set to the things you grouped on in ascending alphabetical order, which is why it goes Adelie, then Chinstrap, then Gen2. But as we discussed, it's ideal to represent this information in a pivot table. It's just easier to look at different combinations. And so let's test that out. Okay, so what are the arguments I'm going to give to pivot table? Well, to match what I have posted in your notebook, how I'll set it up is I'll draw it out so that I have one row per species, so something like Adelie, Chinstrap, and Gen2, and then one column per island. So I might go something like Bisco, it's kind of the same green as my sweater, Dree, Torgerson. Okay, so this is the pivot table that I want to make. How would I do that? What do I set the index argument to make that? It's kind of annoying that I can't keep that up while typing, but that's just a bug in this software that I'm using. How do I make it so there's one row per species? Yeah, I said index to species. And columns to islands. Now here's the tricky thing. You may say, what values are going in the table? Previously, it made sense to set values to body mass G because the things we wanted were average body masses. But here, we're not actually interested in any one of the original columns. We just want the frequencies of these combinations. So it turns out it doesn't matter what you set values to, assuming there are no missing values in the table, which is something we'll talk about next class. But for now, there are no missing values, so let's just pick any one of them. Let's put bill length in millimeters. This is not actually going to be looked at because when I set the agfunc to count, it's not going to take the mean of the bill lengths or the max of them. It's just going to check how many of them are there for each of these combinations. And so I get this back. Okay, and notice if I change this from bill length to body mass in grams, I run the cell, nothing changes. Okay, and so this the values doesn't really matter if using count. Okay, but what do you notice about this pivot table? The original data didn't have any missing values. Well, I didn't prove that to you, but just take it for fact. But this pivot table now does. Why?
Because there are combinations of species and elements that don't exist in the data frame.
Yeah, same reason we saw before. There are no Chinstrap Torgersons. Well, Chinstraps on Torgerson, for example. Okay, which is why when we said, hey, go and look at all of the body masses for that combination of penguins and tell me how many there are, it's like, well, there were no body masses to look at for that combination. So how do I count them up? And so there are solutions to this. One is to use the .fillNA method, which we'll have to also use in homework 3. I could fill the missing values with a 0. FillNA stands for fill the nulls. And there's also fill value equals 0. It's fill underscore value, which handles this without needing to use FillNA. Okay, you'll notice there's a subtle difference between the two. Here, what I have on the slide is a data frame of integers, whereas when I used .fillNA0, there were floats, and that's something to think about. Like, why were they different? Okay, not super important, but something to think about. Okay, the last thing I want to emphasize when it comes to pivot tables is the fact that we started with a data frame whose level of granularity was much more detailed than the result of doing this pivot table. Here's what I mean. When we started, each row of our data frame corresponded to one penguin, right? That's particularly detailed. Once we created this pivot table, each row doesn't correspond to a single penguin. Rather, each row corresponds to an entire species of penguins. Right? So we lost some of the information that we originally had, and so each row doesn't have the same meaning that it did before. Just something to think about. Okay? And it's worth mentioning that in the lecture slides, like if you open the notebook, I have a reference slide on another operation that's similar to pivot table. It's almost like the inverse of pivot table. It's called melt. Okay, I would take the result of a pivot table and turn it back into what the original data frame might have looked like. And I'm not going to spend too much time talking about it right now, and we're not going to use it a ton in this class, but there are some examples there just so that you know that it exists. But before we move forward, what remaining questions do we have about pivot tables? All good? All right. Two other little things I'll show you. One, they have this cool feature built into data frames that you can take the transpose of a data frame by doing .t. So you can reverse what the index and columns are just by using .t. Now, the columns are the species and the rows are the islands. Okay, that's one thing. And then another cool thing is you could actually set index to a list of multiple columns. And you need to do this in homework 3 as well. Okay, so as usual, I'm showing you what each method is for and some of the ways you can use it, but a lot of the nuances, that's kind of for you to figure out while working on the homework, because that's how you'll learn it better. There's only so much you'll absorb by me just saying it here. Okay, any lingering questions with pivot tables? All good? All right. Now we'll move on to perhaps my favorite idea when it comes to data frames, which is that of merging. Okay? So we're switching gears, say goodbye to the penguins. Now we're thinking about phones. Okay? So pretend I have these two data frames, and the one on the left tells me various pieces of information about different cell phones on the market. Okay? So it's telling me that iPhone 16 Pro Maxes, for example, cost $11.99 and have a 6.9-inch screen size, and Galaxy S24 Ultras cost $12.99 and have a screen size of 6.8. So each row on the left is about a phone that just exists on the market. Okay? Each row on the right tells me how many units of each phone I have in the stores that I control. Okay, so on the right it's saying, well, I have Pixel 9 Pros in different stores. I have 10 of them at Arbor Hills and 15 of them at 12 Oaks. Okay, or iPhone 16 Pro Maxes, I have 50 of them at Briarwood. Okay, so each row on the right is also telling me about a phone, but there are duplicates there because I could have the same phone on sale at different places. Okay, and the question I want to try and answer with these two data sets is, if I sold every phone in my inventory, how much would I make in revenue? Okay, and this is perhaps a question we could answer, you know, using a piece of paper and maybe a calculator. I could do things like, hey, well, if I sold all of these 16 Pro Maxes, this would be 50 times, I look up its price over here, which is $11.99, plus, well then if I sold all of these iPhone 16s, that would be 40 times their price over here, $7.99, and so on and so forth. Okay? But hopefully there's some way to do this with pandas. But it's not as straightforward as it might initially sound, because these two data frames have different numbers of rows, and the order of the rows is not the same in both of them, right? The first one goes 16, then 16 Pro Max, then S24 Ultra. This one on the right doesn't even have anything about S24 Ultra, so like, how am I supposed to combine? Okay? And the answer is to use the pandas merge method, or the data frame merge method. And the idea with the merge method is it's going to take two data frames that contain information about the same individuals, here where the individuals are phones, each row is about a different phone, and combine them horizontally when it sees overlap. Okay, so we want to like stitch together the rows about iPhone 16s, and stitch together the rows about iPhone 16 Pro Maxes, and so on. And the merge method is going to help us do that. Okay? When we want to perform a merge, or in SQL terminology, a join, what we need to identify are columns in the two data frames that have overlapping information. And those columns are called the join keys. So there's, in this example, one join key in the left data frame and one join key in the right data frame. Can someone tell me the name of the join key in the left data frame? Hector.
The model.
Yeah, it's model, okay? Model, the model column is the join key in the left data frame, and in the right data frame, the join key is the handset column. So how is it going to merge these two data frames? Well, I'll tell you about the sort of inner workings in just a second. I have an animation we will walk through, but first, before we walk through that animation, I just want to prove to you that it actually works. Not that I think you thought it didn't work, but just so we have concretely how to use it. The way I'm going to use it is by saying phones.merge inventory. Okay, so this is a little strange because there are two data frames involved. One is being called, or one is coming before the dot merge, so we're using the merge method of this phones object, and then one is being passed as an input to the method. Okay, turns out you could do it either way. Phones is the left data frame, inventory is the right, and as we'll see, which one is the left and which one is the right ends up affecting how the resulting data frame looks, and we'll experiment with that. Okay, I also need to tell it which columns are the join keys. It doesn't know that by default. Okay, as we identified before, the join key comes from the model column of phones and the handset column of inventory. So I'm going to say left on model, right on handset. And that'll do what we need it to do for now. Okay, so now I have this one data frame that has the information I need in it. Okay, now with this one data frame, how do I figure out that result? How much would I make if I sold every phone I own? Any ideas? Because now the information is all in one place. I don't need a calculator or pen and paper. Pandas should be able to do this. How do I get it to do it?
Separate each column first and then try and multiply.
Yeah, I need to somehow get it to do 799 times 40 plus 799 times 100 plus 1199 times 50 and so on and so forth. And I can do that. If I extract just the the price column in the units column, I can really just tell it to multiply the two. Okay, and so now it'll give me the amount that I would get by selling each row. What's the total? the sum of those. Okay, so the merge method actually works. It helps us solve this problem. But then the question is, how does it actually work? Like, how did it know which rows to stitch together? Why does this data frame only have 5 rows? Or why does it have 5 rows when this one had 4 and this one had 6? Like, what's actually going on? And once again, we'll walk through another animation. So this is like a presentation within a presentation. I make a lot of these because Jupyter Notebooks don't allow for animations. So this is actually a Google Slides presentation that's imported at the top, and I make it look like it's part of the Jupyter Notebook. Anyways, so here are our 2 data frames, and I've been referring to the phone's data frame as the left data frame and inventory as the right. And the reason it matters which we consider the left and which we consider to be the right is that when it combines the rows, it puts the rows of the left data frame on the left and the rows of the right data frame on the right. So it combines them this way. Okay? Now if we reverse, which was the left and right, well then it would still combine left to right, but the inventory rows would come on the left. Okay? So here's my mental model for how merging works. Okay? And this is important because, I mean, frankly, every exam question you will ever see about merging comes from my mental model of how merging works. Okay? So this, like, following this process is important and will help you resolve any conceptual questions you have with how merging works. Okay, here's what it does. It starts by looking at the first value in the join key in the left data frame, iPhone 16. Okay? And what it does is it scans this right data frame to see, hey, are any of these join key values also equal to iPhone 16? Is the first one iPhone 16? No, it keeps moving. Is the second one iPhone 16? Yeah, it is. And so that contributes 1 row to the output. Okay, but it doesn't stop there, because there could be more iPhone 16s. Is that an iPhone 16? No. Is that an iPhone 16? No. Is that an iPhone 16? Yeah, it is. So it stitches those rows together and puts that in the output as well. Okay? Is that an iPhone 16? No. So it's done and it moves on. Now it moves on to the iPhone 16 Pro Maxes. And it does this exact process again. It's going to look at every row in the right data frame and say, hey, are any of you iPhone 16 Pro Maxes? If so, we have to stitch together and come in the output. Is there an iPhone 16 Pro Max in the right? Yeah, there is. There's one up here. So that gets stitched together down here. Okay, we keep going. Galaxy S24 Ultra. Turns out there are no Galaxy S24 Ultras anywhere here. And so that's why Galaxy S24 Ultras by default don't end up in the output. Okay, there's a way to make it also appear in the output, and we'll talk about that in a bit. But the default behavior of merging is that it won't appear anywhere. Okay. Then lastly, we got to think about Pixel 9 Pros. Is that a Pixel 9 Pro? No, no, yes. So come down here. Yes, come down here. And we're done. Okay, so this is the process that the merge method follows. And it's the process that you should refer back to anytime you're faced with the conceptual question of, like, what happens when I merge these 2 data frames? Now, one thing I'll point out here that we will reinforce with some practice problems in just a bit is that the phone or the models happen to be unique in the left data frame, but they don't have to. Like, there could also be another iPhone 16 here, and if there was, there would be 2 more iPhone 16 rows at the bottom, which would make 4 iPhone 16 rows in total. Okay, so it performs this stitching operation for every element in the left data frame. Okay, we could have also started with the right data frame and done the same process, would have produced the same result. But this is the process that merging follows. Okay, what questions do we have with this idea? Sound okay so far? Yes, Adam.
So, look at the left on and right on. Are those columns on the result always going to have like the same values?
Good question. So Adam's question is, the model and handset columns now seem a little redundant, right? Because they have the same values. Yes, they will. However, if the column happened to be called model in both data frames, there would only be one column in the result called model. Like, it wouldn't have model here and model here. It would make just one model column. But because they happen to have different names originally, they both were brought over and they have the same values, at least in any merge that we will look at. If you take something like EECS 484, you'll learn about this thing called an inequality join, where you could merge when not necessarily the 2 values are equal, but like when they satisfy some relationship, and then they might not be the same, but we're not going to talk about that here. Okay, So here's some details on how the merge method works. I've kind of already described all of this, but here's the key idea that we haven't yet explicitly addressed. There are actually 4 kinds of merges, or equivalently 4 kinds of joins that you can perform, and the default one is what we call an inner join. An inner join only keeps the join keys that overlap between the 2 data frames, which is why there's no Samsung Galaxy S24 Ultra in the output, because it's here and not here. And notice there's also no iPhone 15 in the output, because it's here and not here. So by default, when we do an inner join, we only keep the strict intersection. Okay, and in this context, that might make sense, because like, you know, if I don't know how much an iPhone 15 costs, how am I supposed to know how much it would, you know, net me if I were to sell them all? But you can imagine contexts where you want to keep all of the rows from the left data frame, and if you don't have the matching information from the right data frame, you fill it with null values or some default value. And it turns out we can do that by changing the how argument in merge. Okay, so there's 4 possible things this could be. The default is inner. So if you don't say how equals anything, it does how equals inner. But when I change how to left, right, or outer, it does slightly different things in each case. So when I change it to how equals left, what is new about this resulting data frame? What happens that didn't happen before? Hector.
It added like empty values to account for things that didn't appear on the right side, the right merge thing.
Exactly. It kept every phone that was in models. So this, or sorry, it keeps every phone, or we should say every row from phones. And phones is the left data frame, inventory is the right data frame. Okay? Even ones not in inventory. Okay? And because there is no Galaxy S24 Ultra in the inventory data frame, it doesn't know what its units are and what store it's being sold at. And actually, Adam, notice here, the handset column has a null value too, because there wasn't a Galaxy S24 Ultra value in the original handset column. So that's another way in which these could be subtly different. Okay? But it kept that row in case I wanted to have one combined data frame with every phone that exists on the market. And for the phones that I'm selling, tell me the number of units I have. And for the phones I'm not selling, just leave a missing value. Okay? Okay? What happens if I switch this to a right merge? What's different? Notice there's still no Galaxy S24 Ultra, but there is an iPhone 15. Okay? So this keeps all rows from inventory, even if not in phones. And that's why we have missing values for price and screen for the iPhone 15, because that information was never in the original phone's data frame. Okay? And then lastly, there's outer, which does both of them. It does a left merge and a right merge. It keeps the intersection, it keeps things that are just in the left data frame, it keeps things that are just in the right data frame. And so notice there's an asymmetricness to the missing values. Like some rows have missing units and store values, some rows have missing price and screen values. Okay? So, keeps everything. Okay, notice in each of these results, the number of rows was slightly different. Okay, and it's because the missing values coming, or sorry, the non-overlapping values from the left data frame and right data frame are different. Tussie.
In this class, are we going to be using a specific SQL framework such as SQLite
We're not using SQL. This is all like within the context of Pandas.
within Python?
Yeah, this is, we haven't used SQL, and all of this merging stuff doesn't require SQL in any way. Yeah. Okay. One thing I'll point out is that there's actually a website that helps you visualize what happens when you merge two data frames, and it's called Pandas Tutor. So remember, back in lecture 2 and in the first discussion, we showed you Python Tutor. Pandas Tutor is like the Pandas version of it. So if we click this direct link, it'll help us visualize these exact examples. So let's take a look. My friend made this, by the way. Again, not why we're using it. We're using it because it's helpful. But the way it works is we have some code at the top. Note that I had to like define the two data frames that we're using. So there's code to make the phones and inventory data frames. And what it does is it shows you a visualization of the last expression. Okay, so right now I've uncommented the left one. And you'll notice with the left one, it keeps all the iPhone 16s. It keeps all the 16 Pro Maxes. It keeps the Galaxy S24 Ultra, even though it doesn't exist in the right data frame, and it keeps the Pixel 9 Pros. The iPhone 15, which is only in the right but not in the left, doesn't get brought over. Okay, so feel free to play around with this. And Pandas Tutor, it works not just for merge examples, by the way. You can use it for things like grouping. I personally like our sort of animations a little better for grouping, but you can do things like phones.group by, well, let's do inventory. .group by handset units .sum. Like I can visualize that too and sort of show you piece by piece what's going on. Okay, Pandas Tutor, it's linked in the lecture slide. Cool. So this kind of summarizes the difference between the 4 join types that we've seen. Inner, which is the default, keeps only the rows where the join keys are overlapping. So anything that's in one but not the other is excluded. Left says keep all of the join keys that are in the left data frame no matter what. Right says keep all of the join keys that are in the right data frame no matter what. And outer says keep everything. Okay, and which to use depends on the situation. There's no formula that tells you what the right one to use is in a particular case. Okay. One tip that I'd recommend you use when working with large real data sets, say like in homework 3, in the merging question, is to make a Python set of the join keys. Because this helps you easily see which values are in one column but not the other. Let me show you. So a set in Python is an unordered data structure that only contains unique elements. Okay, so I made a set out of the model column, and there already weren't any duplicates, so it doesn't really make a difference. But notice the order in which it's printed out the elements is different than they were in the series, and that's because sets don't keep track of order. When I create a set out of the handset column from inventory, notice the original column had 6 things in it, but the set now only has 4 things in it, and that's because it doesn't keep track of frequencies. There are no duplicates in a set. Okay? And this doesn't necessarily help you do the merge itself, but it's a nice way to see what values should and shouldn't end up in your merge, depending on if you do a left or inner or outer. Okay, so here's what I mean. If I do left.difference right, what it does is it shows me which elements are in the left, but not the right. Okay? And equivalently, when I do right.difference left, it's not going to give me the same thing. What's it going to give me instead? Tausif.
Which elements are in the right but not in the left?
Exactly, and which one is that here? Yeah, exactly, iPhone 16. Sorry, iPhone 15. Okay, so the way to read this is which elements are in, not the left, we'll say left, but not right. So that's not the same as right.difference left. Okay? So just a tool that I use when merging real data sets. Okay, there are a few reference slides that talk a little bit more about syntax stuff, like what if the column you want to merge on is the index? Well, then you can't say left on equals column name because that's not a column, right? The index is not a column, so there's special syntax for that you can take a look at. Okay, time for an activity. And so I'm going to define 2 new data frames for this activity. And here's the question, okay? And I'm going to give you some time to work on it. And this is the first of what I will call a butterfly method problem. And I'll explain what that means when we take it up. But here's what I want you to do. Open up the question asking form, practicaldsc.org/Q. Take a few minutes to discuss with the people near you to figure out how many rows there will be when we merge these two data frames on the city column. How many rows will there be? Okay, and if you get that one, and remember you're supposed to do this without writing any code, if you get that, follow up and try and figure out how many rows there would be if you merge them on the state column. Okay, remember, you have to pick what the join key is. First I'm saying it's city, in the second slide it's state. How many rows are there in each of these cases? It turns out the answers are different, and I want you to try and work this through with the people near you, and we'll take it up together. Again, do this without writing code. Discuss, I should hear lots of talking. And try and vote at the question asking form. I want to use this more.
Cities with schools? Oh, it's cities with schools. No.
No, it's just like the projects.
Yeah, there's a lot.
No,
There's a
whole
probably
Yeah.
Yeah.
Total.
The syntax for pandas and stuff, so.
Yeah. I'm guessing they do talk about equality joins in 484, right?
Yeah, there's echo joins.
So, showed, briefly talked about relational algebra.
A bit of that.
You can do it by doing cross join and then query join. There's no built-in way of beginning.
So there's 12 Michigans plus 1 Illinois. I think that's right, yeah.
Yeah, there's 13.
Oh, okay. If they get more directions on the step, I'm like, what to do, then I did one day.
This conceptually over inside.
I don't even know what they wrote. There's two in. It did for.
3 Michigan and some more Michigan.
Did you like stop it?
Yeah, because I.
Information from the document.
Okay, we have quite a few answers for the first problem. So let's walk through it. Remember, in any of these questions, you want to replicate the behavior of that animation. Okay, and what did it do? And here the key is we're looking at just the cities. Since we're looking at just the cities, the states are totally irrelevant. Okay, what does it do? It looks at Ann Arbor and says, okay, well, how many of the things on the right are Ann Arbor? Well, there's one here and one here. So that's going to contribute 2 rows to the output. Okay, what about Detroit? There's one there. So those are going to get stitched together. What about Chicago? One there. Those are going to get stitched together. And then our favorite, East Lansing, there's 1. So indeed, the answer is 5. We agree? Okay. Now, the more complicated, perhaps, one is when we merge on state. It's a little convoluted because you see the states, but then you also see overlapping cities, and you implicitly want to use information from the city column to help answer, but everything in the city column is irrelevant here. You're only supposed to look at the states, okay? And here's why I think of these questions as as butterfly questions, or I call this the butterfly method. It's because when you connect the rows for the overlapping state values, it looks like a bad drawing of a butterfly. Why did I connect these 4 lines? Well, I was connecting this Michigan with all 4 Michigans here. We agree? Okay. Make a colorful butterfly. Now let's look at this Michigan. What am I going to connect this one with?
The 4 Michigan.
The same 4 again. Okay? 1, 2, 3, 4. You kind of see the butterfly wing? Kind of a butterfly. Don't see. Okay, let's pick another color for Illinois. Just one lone winglet, I guess, and then Michigan, that's going to give us another 4. Okay, we get another 4 for Michigan. So what does the result end up being? 4 plus 4 plus 1 plus 4, which is 13. Do we agree? Okay. Now, it's good that we're able to calculate this on our own, but we should take a look at what the resulting data frame actually looks like. A lot of the rows in it don't make any sense, because all I said to combine on was the states. Okay, so it's going to combine things like Ann Arbor, Michigan with, you know, Wayne State University, Detroit. And that exists right here. It doesn't really seem like there's a reason to combine these two, but when you say merge on just the states, it does that. Do we agree? Okay. Now here's a trivia question. What's going on here? I didn't say what to merge on. And let me show you these side by side one more time. I didn't say what to merge on. What did it do? Any guesses? Colin.
Merged on cities because the city columns named the same between the tables? Or is that that's the first one? Sorry.
What it actually does, and this might be a bad illustration of it, is it merges on all shared column names. So it combines the rows that have the same city and the same state. Okay? It merges on all shared column names. So in this case, it combines the rows with the same city and the same state. Now, in this case, it looks like it just merged on city because we don't have any instances of the same city name in different states. But like if we had a Detroit, Michigan and a Detroit, California, you'd be able to see the difference here. Okay? But the key idea here, and again, this comes up in homework 3, I would think we give you a hint there. You can merge on multiple columns. Okay, and what it does is it combines rows where both of the values in the 2 columns are the same. Okay. Good. And so, whatever, you critique my artistic ability, but the general idea of these sorts of questions I call butterfly questions, or the butterfly method, okay? And again, called butterfly because they kind of look like a butterfly wing when you connect the lines. But the conceptual idea is when you're asked to find the number of rows that appear when you merge 2 data frames together, there's actually a formula that you could use to figure out the number of rows that are in the output. Okay? And it ends up being, you count the number, you know, in that last example when we merged on just state, what we did is we found the number of Michigans in the left times the number of Michigans in the right, plus the number of Illinois in the left times the number of Illinois in the right, and so on. And if we had other states like California, we would do number of Californias in the left times number of Californias on the right. And we sum all of these count multiplications together. Okay? And so all of these questions are kind of answered similarly. And so I really like these kinds of questions because they, you know, involve thinking both about Pandas code and also conceptually about this idea of how data sets are joined. And you'll see a lot of them in this week's discussion. Okay? So for example, here's a question that I would consider a butterfly method question. But it's more abstract than anything we've looked at in lecture because you don't actually know what the data set looks like. All you have is that there's this data set, and in the join column, there are 2 values equal to DTW, 4 or 5 equal to ORD, and 3 equal to MKE. And the question is, when you merge this data set on itself, how many rows are there? Okay, and you can answer the question, and this is something, I'm not going to give you the answer now because TAs are likely going to walk through it in discussion tomorrow, but this is what I mean by a butterfly merge question. Okay, these are common, this worksheet is filled with them. There's lots of them in here. Okay, this is another related butterfly merge question about the union, several of them in here. Okay, so you'll get lots of practice with it, but I wanted to explicitly call it out as like a thing in this class, and likely, though I don't know yet because I haven't written it, a thing on the midterm. Okay, and this formula may seem unintuitive, like where did it come from? It's a direct consequence of walking through this animation that we saw earlier. Okay, I was just generalizing the pattern that we already saw. Okay, any questions with the merge method before we move forward? Feeling okay with merging? Okay. So I'll give you context. For homework 3, which was just released, the first set of questions, questions 1 through 2 and 3, are all about elections data. I made the homework initially in like October of last semester when we could say things like, oh, the election is coming up, let's analyze 2020 data. So of course we had to update that this week. So now it uses 2024 data and says, oh, the election was a few months ago. So you get to draw like a cool electoral college map, like the ones that you saw on the news, where you like color different states based off of, which party won, and then you like tally up a number of electoral college votes. And it turns out to do all of that, you need to use group by in some complicated way. So questions 1, 2, and 3 involve group by. Question 4 is all about merging, and question 5 is all about pivoting. Okay, so it's all stuff from today's lecture. And then question 6 relates to pivoting, but it's a more theoretical question. Okay, the last idea I want to talk about is that of transforming. And to do this, I'm going to introduce yet another data set. So I know we're dealing with a lot of data sets here, but this data set we're going to see quite a bit. For the rest of today's lecture, we're going to see it all of Monday's lecture. I'm going to post another guide about data visualization over the weekend. We're going to use that there as well. And it's going to come up again in homework 4. So we're going to see this data set quite a bit. How many people have heard of the financial platform Lending Club? In what context have you heard of that?
It's like an anti-poverty thing, right? Is that where people are lent money to start lives like in Africa and in like developing nations?
They may also do that, but that could be what they used to do. It's a platform where you can just apply for a personal loan. Okay, and the way that they used to work is that they were a peer-to-peer network where I could say, hey, I have extra money lying around, let me invest it in the platform and lend it to someone else and they'll pay me back with interest. They got rid of the peer-to-peer nature of it, but it's still a place that you can go to for personal loans. Okay, and so we're gonna use a data set of actual loans from the Lending Club for the next lecture and a half. And the data set we have is still pretty big, has 6,300 rows, but the full data set, which you can likely find online, is over 300 megabytes in size, and so doing any operations is, are quite slow on it, and we don't really need that for the purposes of what we're illustrating here. But even with 6,300 rows, that's way more than we could, manually inspect. And so one tip that I often use when working with a really large data set is use the sample method on it repeatedly. What this does is it just picks a random subset of 5 rows. Each time I run it, kind of like np.random.choice or multinomial, things that you're sort of familiar with now from homework 2. Each time you run it, you get back a different subset of rows. Okay, so it gives you a taste of what kinds of things you're going to see in the columns. Speaking of the columns, there are many of them here, and the preview is only showing me like the first 4 and the last 4. So a good tip is also to use the columns attribute to get a preview of what the columns actually are. Right? There are some potentially interesting things like the interest rate, FICO range low, which tells me the credit score of the person with the loan. I have the loan amount, how long the loan was for, interest rate, their job title, and so on. Okay, and again, if I use .sample repeatedly, I'll get different subsets of the data. Okay, to clarify, these are not loan applications. These are people with actual loans from the Lending Club. So anyone in this data set already had their loan application approved, and they actually have a loan. Okay? And so next class, we will think more about what kinds of questions we should ask when we're first given a data set that we don't know all the details about. Like, one question is, what is the maximum possible loan amount one could have gotten from the Lending Club? The answer ends up being like $30,000 or $40,000, and you can verify this by using the describe method on the loan amount column. You can see the max was 40,000, the mean was around 15,000. So this is not a place you could go to like mortgage your house, right? Because house mortgages are way more than $40,000. But if you have credit card debt you want to pay off, I guess this is a place you could go to. And so we'll talk about this process of like asking the right questions given a data set on Monday. And that's called exploratory data analysis, and that's where visualization comes in. But for today, I want to focus a little bit more on the technical aspect of data cleaning. Okay, so as I mentioned at the start of the lecture, transforming for now will just be this act of using a function on every element of a series, okay, or every element of a list or array. And this is something we often need to do when we're given a raw data set to prepare it for numerical analysis. Like, for example, if loan amounts have the $sign in them and they're stored as strings, well, then we couldn't do any math with them because they're stored as strings. So we need to get rid of the $signs and convert the types from floats to ints to be able to work with them. Or, maybe if we want to use formulas that require metric units, we have to convert things from feet to meters. Or, you could imagine strings in which the important information is just a substring within the larger string. Maybe we need to use some sort of techniques like regular expressions, which we will learn about in the coming weeks, to extract relevant pieces out of the string. Okay, so one example is like, if I want to find, or I want to do some math with the length of the loan, I can't do that right now, because instead of 60 and 36, corresponding to 60-month or 5-year loans and 36-month or 3-year loans, I can't do any math with those numbers because they're stored as strings. So somehow I would have to get out the number 60 from the string 60 months, for example. Or like, another issue is that if I look at the employment title column, there are lots of equivalent ways of a lot of duplicate but equivalent ways of representing the same thing. Like, registered nurse is one of the employment titles, but so is, say, nurse, and so is RN, which stands for registered nurse. So if I wanted to do something like figure out the total number of nurses that were given loans in my data set, well, it'd be kind of hard to do that because there are a lot of different ways of representing the term nurse, and not all of them contain the word nurse themselves. Okay, so these are the sorts of things we'd have to deal with in the context of data cleaning, and the solution ends up involving doing some sort of cleaning process to every element in a column. Okay, so one way that you can use an arbitrary function on every element of a column is by using the series apply method. Okay, this is different from the group by apply method we learned last class. Okay, this is a more general apply method. You can call it on any series you want.
Either a group by series.
Well, you can use it on a group by, like a data frame group by or series group by object, as we saw last class, but it also works directly on series and data frames. And so, for example, if I want to take a string that's like 60 months and turn it into just the number 60, how could I do that using string methods? And this function I'm trying to define is going to take in one string and return one string. Tiger?
Split by space.
Good, I can split the string, get the first element, and then I need to convert this to a number. Okay? So that's how I would do it in the particular case of 60 months, but I need to define this more generally in a way that I take in one string, return one string. So I'll say something like, take my term string, split it, get the first element, and then convert that thing to an int. Now when I do something like clean term 544 months gives me 544, or clean term 36 months, that works. Okay, now that I have this function, note that this function takes in one string, returns one number. I can give it to the apply method. So as an input to the apply method, I'm giving a function. okay? And what it does is it automatically uses this function on every single element in the series, okay? And I'll emphasize here that clean term itself maps from string to int, okay? Now, like I mentioned, there's an apply method that also works for data frames, which we haven't seen an explicit example of, but it exists. And there you have to specify, well, do you want to use this function on every row of the data frame or on every column of the data frame? You have to specify, do you want to do it axis 0 or axis 1? It's the kind of thing you'll explore in coming homeworks. And then there's also an apply method in the context of group by, and that does something slightly different. But in general, the apply method is how you use an arbitrary function on a collection of things. Okay, this is how you use it in the context of cleaning strings. The issue, though, is that it's not so great efficiency-wise. Under the hood, all it does is just call a for loop, calling your function repeatedly. Okay, and it just stitches the results together. And we can prove that by, again, going on GitHub, searching up the pandas repository, and looking at the source code. You can see this yourself. Okay? In fact, here, when I used my time at CellMagic, it actually is slower on average than using a for loop somehow. Okay? On average, it took 1.03 milliseconds instead of 902 microseconds, which is smaller than 1.03 milliseconds. Okay? So using apply, it works, but since it's so general and needs to be able to support any kind of function, it's slower than other more efficient techniques that are designed for specific use cases. Like, for example, if what you want to do can be done by just using numerical or number operations directly on a series, do that, because that's way quicker than using apply. So for example, here I'm just using some arbitrary mathematical operations. I'm doing integer division by 10 and then multiplying by 10. Effectively, this rounds down to the nearest multiple of 10. And when I do these operations directly on the series, it only takes 52.2 microseconds on average, versus if I put the same function in .apply and require it essentially to for loop over every element in the series, that takes 10 times on average more time. Okay? So moral of the story is, apply exists, but there's often a more efficient way around it, especially if what you're doing involves number calculations, numeric calculations. Okay, so avoid .apply if you're working with numbers. Sound okay? Now it turns out that there's another related tool in the context of like doing things to every element of a series, and it's what we call the str accessor. Again, I'm using this weird term. It's not a function, it's not a method, it's an accessor, and I'll show you how it works. Okay? And you've actually already seen it before. A few lectures ago when I showed you about this thing, str.contains. Okay, and you were playing around with that in homework too as well. Here's how it works. You start off with a series, like lone term, and then after it, you put .str. Okay? That alone doesn't do anything. But after that, the .str, if what you put is some operation, it's going to use that operation on every element of the original series, assuming those things are strings. Okay? So if I do .str.split, it's going to do the str.split operation on every element of loan's square brackets term. Okay? So it's using it's using the split method on every string in loan's square brackets term. Okay, which is why when I started with the string 60 months, I now get back a list with 60 end months. Now, this is a quirk of, I'm guessing this is your question, why are there no quotes here? Okay, well, one may ask, why are there no quotes here? And that's just a quirk of how Pandas renders these things. But okay, yeah, what was your question?
I was just curious, what would happen, would it just throw an error if we ran this on a column with like mixed data types?
Well, we're about to actually find out. What if you put .str after something that doesn't contain strings? Well, the answer is sometimes it works, sometimes it doesn't. Okay, so let's go to loans. I don't know, let's pick out the IDs. Are those strings? No. If you do .str, doesn't like that. Okay, it says you can only use the str accessor with string values. But it can be a little inconsistent in that regard. For example, this series itself isn't made of a bunch of strings, but it doesn't bark at us when we do .str after it. In fact, it actually is useful for what we want to do. Even though this series is made up of a bunch of lists, not strings. But as we first saw in lecture 2, lists and strings kind of work the same way in some ways. Like they're a sequence of things that you can index into. And so .str also works in the context of lists. So if I wanted to, in one line, without using .apply, get out the term numbers as ints, I could do this. And that does all of that in one place. Okay, and it uses .str twice. But here, if we treat this as one series, what this does is it indexes into the 0th element on every list in the one series, which is why when we went from this list of 60 months, we now came down to 60. Okay? Now you may say, hey, okay, this is complicated, at least it better be efficient. Turns out, no, it's even worse than using .apply, which was already worse than a for loop. But it's way more concise than using a for loop, and it's the more Pythonic or Pandas way of doing it. And so because it comes with this concision, we tend to write code like this, even though it technically is slower, unless you're dealing with a data set with millions of rows or something, in which case you're likely not using Pandas anyways. You're going to start with SQL, query the data you want, and then bring it to Pandas. Okay? But just these are all tools that you can use when necessary. Okay? The last aspect of transforming data I want to cover is working with timestamp data. Okay? Or data that refers to dates, times, days of the month, hours of the day, those sorts of things. Okay? By default, when you load in a data set using pd.read CSV, date information is going to be stored as strings. Okay? So like these strings of June 2014, December 2016, so on and so forth, they're stored as strings. But it turns out that there's a pd.toDateTime function. Okay? And this function takes in an entire series and gives you back a series of datetime objects. So this is a new Pandas data type that we haven't seen before. And this is the kind of idea we spoke at length about in the linked guide about data frame internals. The Pandas data type of this series is datetime. Each element. Okay. So this example happened to work right away, but sometimes it can't automatically infer how the date was formatted in the original series, and so you need to specify a format string. And these format strings are kind of nasty in how you specify them. I think this one is lowercase, or %b dash %y or something like that. There's no reason that you would already know how these work. The documentation describes how they work exactly. But like capital %y means a 4-digit year, whereas lowercase %y likely means a 2-digit year or something. Okay? So what's the benefit? Well, now that you have your dates as datetime objects, there are datetime related methods that you can use. So for example, I could do .dt.month, and now it automatically can figure out what month it was of the year. Okay, or like dt.monthName, I believe, is a method that I could use. Okay, and notice it's not just taking the first 3 letters here. Like it knew that it was actually December, even though the initial string just had DEC. Okay, And down here, it doesn't say anything about the string November or December at all. So it's doing more than just string formatting. It knows how to work with date objects. Okay. One last thing I'll mention is that there's this data frame pipe method, which I like to use when doing lots of data cleaning steps, but it can be kind of confusing when you first see it. Okay. Here I've defined two functions, both of which take in a data frame and return a data frame. Okay, so this takes in a data frame and returns a data frame. And the way I've structured my code here is that each of these two functions does one of my two data cleaning steps. Okay, the first one converts the term names like 60 months and 36 months to integers of 36 and 60. And the second one does the formatting of the dates. Okay, so I could go to my original data set and pretend this was all at the top of your notebook. I could go to my original data set and call the first function, clean term column, on it. And so now the term numbers are fixed. And then I could call the second function too, clean date column. But you can see that this is getting kind of ridiculous. Like what if I had 5 more data cleaning functions I wanted to call? Then I'd have to like have 5 function compositions in one step. Okay? So the pipe method comes to our rescue. Essentially, it allows you to replicate this behavior the pandas way. How do you do it? Well, you use the pipe method, and as an input to the pipe method, you put the name of the function you want to use. Okay? So now this function itself takes in a data frame, returns a data frame, and by using pipe, it just uses this function on that thing and gives you back the new data frame. Okay? You can do dot pipe again, clean date column, and now I have the date column. Okay? So essentially these are equivalent, but I think we'd agree that the first one is easier to read. Okay, there were a few more details about working with timestamps that were in the lecture that I didn't get to show you. Like you can, well, we'll hop over to the HTML. I'll just point it out here because it's not super crucial to bring up next class. But for example, you can do things like group by every 6-month period. Okay, because it all like datetime objects can do math on like how far apart 2 dates are in terms of months. And so I can say something like, hey, for every 6-month period, go to the interest rate column and take the average. Okay, so it's like a version of group by, but for times. Okay, and you can imagine how that might be useful when wanting to draw like a line chart to look at how the interest rate has changed over time, for example. Okay, that's it for today. Remember, we have discussion tomorrow, homework due on Tuesday, and that's about it.